Okay, so last time we talked about the virtual memory, and using the virtual memory, we can have potentially allocate more logical memory space than the physical memory space. Because with the local virtual memory, we can use some kind of technique called demand paging. Demand paging. So in the demand paging, we can actually only allocate the pages that we are actually using. So for example, we initially when we try to actually execute a program, when we try to execute the first instruction of the program, and then we're going to check where this instruction is located. We check the memory of this instruction, and with the memory address, we can look at the first part, the page part. So we find out, okay, so the first part shows which page this instruction is located in. And then we check the physical memory to see whether this page is loaded into the physical memory. We check this by checking the page table, because when we build a page table, we basically just list the page number and the corresponding frame number, the page frame number. Okay, and then we have something called present bit. Okay, we have something called the present bit. Okay, I need to set up a pen so I can write. So this present bit basically shows whether this page is loaded into the physical memory yet. So in this particular case, in the diagram, so this is actually the program. Okay, this whole thing is a logical memory and a virtual memory. So, and we find out when we start the program from the first instruction, and then we find out, okay, this instruction is in page 0. And then we look at the page table and find out page 0 is present, right? It's already loaded into the memory, in the physical memory, because the present bit shows it's 1. And then we look at the corresponding page frame number. Now the page frame number basically shows this is in frame number 2, right? So we actually pointed to the frame number 2. So then, based on the memory mapping, we can actually map this memory into this physical memory location. Okay. Now, since this is the first instruction in page 0, and this correspondingly, this is going to map to the first, instruction in frame number 2. Okay. So the location of this memory address in the page is called offset. Okay. So then we can actually start to execute the instruction one after another most of the time. And then suddenly we run into an instruction which is located in page 1. Okay. And then the operating system is going to check the page table and check the page 1 and find out this page 1 is not loaded. Okay. Now in this case, we're going to have something called, what is this called? If we try to execute an instruction which is located in page 1, and the page 1 is not physically loaded into the memory, and what is this called?
Page fault.
It's called a page fault. Thank you. Now, when page fault happens, the operating system is going to check the physical memory to see whether I can find any free page frame if I can find a free frame. Now, if I find a free frame, then I basically load the page into the frame, update the page table. Okay, so in here, if I find a frame like say 4, okay, I choose 4. I just deliberately choose the frame that is not connected to page the frame number 2. Okay, so I choose page 4. The frame number 4. Sorry. So then I map this in here, and I update the present bit, right? So that's what I'm gonna do. And then, so for this particular instruction, then I just restart and execute the instruction over here. So that means if I actually keep execute the instruction in page 0 and suddenly jump to page 1, then in the physical memory, I'm gonna actually fetch the instruction in this order. And suddenly I jumped here, okay, because this page 1 is loaded in frame number 2 or frame number 4. So this is how the demanded paging works, okay, which is fine. Now, then we may run into a kind of situation, because remember, in demanded paging, the virtual memory could be potentially larger than the physical memory. So there's a possibility that when actually page fault happens, which means when the program tries to load a page into the physical memory, and we find out the physical memory is full, it's not available. Now, in this case, then we have to do something, right? Either the program just wait, say, sorry, I want to run the instructions in this particular page, and the page is not in the memory, physical memory, and the physical memory is not available. So I cannot load the page into a physical memory. So I have to wait. So that's one solution. But most operating system try not to use that option, because when I actually run a program, okay, and execute the program at this moment, and suddenly the program stopped. It says, sorry, there's no physical memory. So this is not acceptable, right? Most of the time, if the program is currently running, we want to make sure the program continue to run. So in that case, then we have to load the page into the memory, but the memory is not available. So then we need to pick some of the pages that is currently in the memory, okay? And we just swap it out. So then we load, and once we swap this page out, and we free the memory, and we load the page into the memory location. So that process called page replacement. Page replacement will guarantee that this program will continue to run, because once actually the program is actually try to execute a particular instruction, and the instruction is locating the page which is not loaded, and then we just say, okay, we have to load the page, and then if the memory is not available, we pick one of the one of the page which is currently in the memory, swap it out. We just take it out from this particular frame, and we free the frame, and then load the page into the frame, and then we update the page. We update the page table. So technically, we have to update the page table twice, right? Because when we pick a victim, so we find out, okay, that particular page, whatever the page number is currently in friend number 11. So that page should be recorded in the page table, which shows that page is mapped to friend number 11. And the present bit should be 1, right? Now, when we remove the page off, take the page out of the friend, and then there are a couple of things we have to do. We have to update the page table on this part. So we're going to actually, once we remove it, we change the present value for that particular page into 0. Okay, if the page is, say, page 100, which maps to friend number 11. And we want to remove page number 100 so we can accommodate page number 10. Okay, so once we remove page number 100, page 100 off the frame, and then we have to update the information. And also, we need to check whether that page 100 has been modified. Any actually, memory location in that friend number 11 has been updated. Okay, sometimes that particular page happened to actually store a data, right? So temporary value, anything like this. So then if the value has been changed, then before we actually remove it from the friend number 11, we have to make sure, that page 100 should be copied back to the virtual memory. Okay. Once we copy back to the virtual memory and then remove it, and once we remove it, we update the page table to mark the page 100 as not mapped. So that means the present bit should be changed to 0. And then we load the page 10 into the friend number 11, and update the page table and mark page 10 mapped to friend number 11 and change the present bit to 1. So so you have to change the page table, twice. First, change the table for the page that will be removed, and then change the page table information for the page that will be loaded. So we have to do this twice. Okay, so this is something called page replacement. Okay. Now we're going to talk about the page replacement, more, and then we're going to actually even talk about how we're going to replace the page, because when we choose a victim, so if physical memory is full and the page fault happens, we have to replace the page, and then which page we should remove. Okay, then there are a couple of different algorithms to do so. The best idea is when we try to remove a page, we have to make sure that this is going to have no big impact to the performance. Okay, now one of the example is, so it's like the worst scenario is, okay, we want to load the page and we have to do the page replacement. Okay, page 10 wants to be loaded. Okay, and then we just pick a page 100. Okay, which is currently in friend number 11, just like I say. Now, once we removed page 11 or page 100 off the friend number 11, and we update the page table, we did all this job and update the page table, so make sure the page table is current. And then we load the page 10 into friend 11. And right after we finish this job, and immediately the page 100 is referenced. And then we find out page 100 is not in the memory. Actually, it was in the memory, but it was removed. Just not long time ago, it was just removed. And then we just reference the page 100 again. So that means we're going to do another page fault to load the page 100 back, right? And then we replace another pages and remove the pages. And that page, which was just removed, was referenced again. And then we have another page fault. That's really a bad situation, because with that page replacement, we actually increase the page fault. The page fault is very costly because it requires to, load the page from the hard disk. Okay, so this is very costly. So that's something we need to talk about. We need to design an algorithm for the page replacement, that this algorithm should reduce the impact. Okay, because when we have a page fault, there's always a cost, because you have to actually, remove the page and then load the page from the physical memory, and there's a performance issue. But what we try to do is try to reduce the number of page faults. Okay, if I have two, now when we judge which page replacement algorithm is better, we basically judge by counting the potential number of page faults. If that algorithm leads to fewer number of page faults, that's a good algorithm. If that algorithm actually leads to a lot of page fault, that's a bad algorithm. Okay. So before we actually switch to page fault topics again, let's actually talk a little bit about the paging of tables. Okay. Why we want to talk about this? Because what virtual memory can be very big. So virtual memory can create address space which is much larger than the available physical memory. Okay. Now, in modern days, the programs becomes bigger and bigger and bigger. Okay. This is not a, avoidable. When the physical computer system becomes more and more powerful, and then the memory space becomes bigger and bigger, so then you may actually require a big memory address. So you need more extra bits to store the memory address. Now look at some modern computer systems. We may have a software that takes like a 100 million lines of code. Okay, or at least that illegal 10s or 20 million lines of code. Okay, so well, people just make some kind of estimate that if you look at some of the software installed in the fighter jet, like the fighter, the airplane. So the most recent fighter jet, like F-35, there are actually more than like 10 million lines of code. That's a lot of actually space, 10 million lines of code. Okay. Now, when we look at the previous generation of fighter jet, it was probably about 1/10 of the current size. So the modern actually airplane actually rely heavily on the software. So that with the big program, so we actually requires a big virtual memory space. Okay. Now let's take a look of an example, like a modern PC. We use like a 64-bit virtual memory address. So we're going to use 64-bit virtual address. With 64-bit, how many memory addresses we can represent? You may need a 2 to the 64 memory address, right? So the memory address use 64-bit. Now let's say, okay, So that's someone just did the calculation and find out 2 to the 64. What does that mean? Okay, so that's, I don't know, what is this? So that's, 1,000, million, billion, trillion. Oh, that's, man, that's big. Now suppose we use 12 bits. We use 12 bits for the offset. What does 12 bit means? That means for each page, if we use 12 bits, and then if we use the current page scheme, then 12 bits used for offset, and then we're going to use 52 bits for the page, for the pages. Now, how many pages we're talking about? We're talking about 2 to the 52 pages. That's a big, right? And then for each page, how big is each page? Each page actually takes 2 to the 12 memory address. Memory addresses. Okay, 2 to the 12. That's big, right? So for each page, it contains 2 to the 12. Yeah, 12 bits for the offset. Okay. So then the remaining 52 bits. Okay. That's a lot. Okay. So now in modern days, people try to say, well, that's not gonna work efficiently. So they actually split the 52 even further to half and a half. So the first half, 52, split into half, that's 26. And that's another 26. So then we actually, instead of using a page table that, we basically going to create 2 levels of page tables. Okay. Now the first level, first 26 represent the pages of tables. Okay. It's not, so we basically just to create something called a table of the table, So then when we actually refer, any address here, 26, that's still a lot of number, right? 2 to the 26, that's a lot. Now, for each item in here, it's going to map to 2 to the 26 different tables, 2 to the 26 different table. And each table is going to map to, each table is going to refer to a frame size of 2 to the 12. So that's called actually table of the table, So the table does not actually map the page to a frame. That first you're gonna go through 2 levels. Okay. So that's basically the actual implementation for modern computer system. So I'm not gonna actually expand the topic, but if you want to know that, and you can actually refer to more information. The Zai book actually presents some of the information, but I'm not going to cover that information. Okay. So just to let you know, modern days, in the page table, we don't just split the page table into the offset and the page. And then in the page, we're going to split into even further to 2 levels of pages. Okay, page number. So that's why we have S and P. Okay. So there's a S, P, and a W. That's the offset. So you have 3 levels. Okay. Now with the physical memory actually continue to grow, it's possible that we may actually split the page not into 2, but probably into 3. So we have a page number referred to a whole bunch of page table, and another page table, point to another, whole bunch of page table. So it's just like a tree structure. Okay. Okay. That's about it. That's all I want to talk about. So we are not going to test you on this paging of tables. Okay. Now let's actually come back to the page replacement. Okay. Now in the page replacement, we know that so for the program, we divide it into pages. Let's assume that there's only one level of page, not the page of page. Okay. And then the physical memory, we divide it into a frame of the same size. So page size, frame size are the same. So we don't need to worry about anything. Now, if the page, so when we start the computer program, let's say the first instruction, which is actually from the main program, main method, okay. And then the page 0, the instruction in page 0 is called. So now page 0 is not in the memory. So then we basically build a table, page table. So let's say the program actually has 6 pages. Okay. So we're going to build a page table. And maybe continue. Okay. Now, so if the page 0 is actually referenced, first instruction in page 0 is referenced. So then we actually check the page table. And initially the page table says, so that's present bit. Okay. So initially, the present table is 0. So that means for page 0, there's no frame number mapped to page 0. So then we're going to find a frame number, and then we find a frame number 3, right? So we load the page into frame number 3. Page 0 is loaded into frame number 3. Okay. And then we update the page table, update the present bit, and all these, the rest of all 0. Okay. So now when we continue to execute the instruction, as far as these instructions are still in page 0, we're in good shape, right? Because then we're going to map each of the instruction into the actual physical memory, and these are the actually instructions that will be loaded into the physical memory. So we're in good shape because page 0 is already in the physical memory. So this basically says, once the page is loaded, every instruction in that page can directly fetch from physical memory because these instructions are already loaded. Now, suddenly, we run across the page 0 to page 1. Okay. And then this is going to actually lead to another page fault. If page 0, page 1 is not in the physical memory, and then we find out page 1, the present bit is 0, so it's not in the physical memory. And then we find another frame, right? This frame, we find this frame. Say this frame is available, and then we just map the page 1 friend number 1 and the map to here, update the page bit. So we load. So here, when we execute the first instruction in page 0, it calls the page fault, right? And then we execute the page instruction in page 1, it calls page fault. And then the follow of the instruction in this page 1 will not cause any page fault because page 1 is already in the physical memory. Okay. Now, suppose when we execute the instruction here, and suddenly we want to execute the instruction in page 3. Not, continue in the consecutive location, but we jumped. Now, which is possible, right? In certain case, like if we run like a branch, like if statement. Now, if something happens, if condition is true, then we're gonna actually continue to execute the block over here. Now, if the condition is not true, then we're gonna skip to else phrase, right? We go to the else phrase and execute another block. Now, if there's a branch, say if else if we have a programming that the execution may not actually follow the certain order. It may actually jump from one place to the other. So in that case, then we have a page fault when page 0 is loaded, and then we have a page fault when page 1 is loaded, and next one we suddenly jump to page 3 at a certain location, and then we find out page 3 is not in the memory. So we're gonna actually find the page 3, find the physical memory. Okay, here's friend number 4, friend number 5, and then we find the friend number 5. So we load page 3 into friend number 5. We update, right? So now we can find the order of page reference, and that's called a reference string. So in this particular case, the reference string is like a 0, 1, 3. So we load the page 0, and we have a page fault, and then we have a page fault, and here we have another page fault when we load the page 3. And after page 3, we may actually jump to page 5, right? So then the next page we want to load is page 5. And then after this, we may go back to page 1. So then we may go back to an instruction in page 1. So at the time when we actually come back to page 1, now page 1 may or may not be in the memory anymore, right? Because if you actually execute this, and then we actually execute instructions in other pages, and suddenly we want to come back and say page 1, and hopefully the page 1 is still in the computer memory, in the physical memory. So we can continue to run the page 1 without incurring any page fault. But who knows? Maybe during the execution of page 2, page 3, page 5, and page 10, page 100, after a couple of execution in other pages, and we come back to page 1, and we find out that page 1 has been replaced. So page 1 is no longer in the memory. Now then we're gonna have another page fault to bring the page 1 back, right? But hopefully page 1, because it was loaded, not just most recently it was loaded, and hopefully when we come back to page 1, and page 1 is still not replaced, so it's still in memory, that's a good case, right? The bad case is page 1 has been replaced, so we have to load the page 1 back with another page fault. So then the order of, page reference is called the reference string. When we talk about the page replacement, we don't really care about a particular memory. We actually care about the page reference string. So the page reference string is a sequence of page numbers referenced by executing program during the given time interval. Okay, reference string are used to compare different page replacement algorithms by counting the number of page fault generated. So what matters is that when page replacement involves, then we only care about the page reference string. Okay, so if the page reference string is like this, so when you execute here, page 0 is load, the page 1 is load, and then we jump to page 3. So page 3 is actually, and then we jump to instruction in page 5. So page 5 is loaded. And then we go back to page 1 and we have next one. And after we execute the page 1 and we go to page 3 again, page 5 again, and come back to page 1. So 135, 135, 135. That's typical. Like if we have some kind of a while loop, right? If in a while loop, you may actually continue to run some kind of circle, or we may actually have different page reference string. So the page reference string may actually varies. So now when we study different page replacement algorithm, we only focus on the page reference string. Okay. Now this is actually a typical example of page reference string. So when you actually run execute the instructions, and this is the first actually virtual memory we refers. And then we find out, okay, so you use 4 bits for the pages and 12 bits for the offset. So then when we actually refer to this memory and we check the page number, it's 0. Okay. And the next instruction is in this memory location. And then the page is still 0. Okay. So if the next instruction is still page 0, then we don't repeat the page 0 because we only refer the page number once. Now for all the consecutive memory, which is actually located in the same page, we just refer the page number once. Okay. And then suddenly 1, 2, 3, 4, and after this instruction, which is still located in page 0, and next instruction we're going to execute is 0010. So that's actually page 2. And then the next instruction is still in page 2, still in page 2, still in page 2. So then we're going to actually only put the page 2 once. Okay, so that's the next page reference. And then we jump to page 3, and then we come back to page 0. Okay, and then we go to page 9. So then we find out the page reference string is 02309. 02309. Okay. The reason we do this is because once the only possible page fault may happens at the very beginning. Okay. If you actually try to refer to the memory address, this memory address, and this memory address is page 0, and that's the only possible chance that the page fault may happen. If that page 0 is not in the memory, and then we have page fault, right? And once we have page fault, and for the follow-up memory access, there will be no page fault. So page fault only happens at the beginning. And the page fault only happens at the beginning. At the beginning. At the beginning. At the beginning. It may happen or may not happen, because if we try to come back to page 0, and fortunately, page 0, which was loaded into the memory in the first page fault, in the last page fault, and that page fault actually forced the computer operating system to load the page 0 into the physical friend. And when we actually refer to page 0 again, and it's page 0 is still in the memory, and there's no page fault. Page fault happens only when it was loaded into memory and replaced later on. And then you have to do the page fault again. So it's possible that there might be no page fault. But if page fault happens, it always happens at the beginning. Okay, it's always happened at the beginning. So that's why reference string is important. Any questions? Now, next couple of slides, we're going to talk about various different algorithms, the page fault replacement algorithms. If we are unfortunately, if we try to we have to replace a page, then we need to actually figure out what page should be replaced. Okay. The first page replacement algorithm is called optimal. Okay. If you look at the name, we know that must be the best page replacement algorithm, right? It's optimal. So let's take a look. So here's the model, the example we use. Okay. Now this is the page reference, the reference string. Okay. So we have a page 0 happens at the first, and then page 2, page 0, page 3, page 1, page 4, page 1, 0, 1, 2, 3, 0. That's the page reference string, okay, for this particular algorithm, for this particular program, I'm sorry. Now, suppose the physical memory, for the physical memory, we only have 3 friends or 4 friends. Friend number 0, friend number 1, friend number 2, friend number 3. And initially, friend number 0 is currently accommodate page 0. Friend number 1 accommodate page 1. Friend number 2 accommodate page 2, and friend number 3 accommodate page 3. Okay, so looks like when we try to execute the program, we execute the instruction in page 0 first. So we load the page 0 into friend number 0. And then we continue to execute the page number 1. And then we load the page 1 into friend number 1. And the page number 2, we load it into friend number 2. Page number 3, and we load it into friend number 3. So now the physical memory is full, right? Because all the frames are occupied. So the memory is full. So then we gonna have the page reference string like this. The next page we will reference to is page 2. So if the reference page is page 2, do we have any page fault?
No.
No, because page 2 is in friend number 2. So it's already there. So we don't change any configuration. So page 0 is still in friend number 0. Page 1 is still in friend number. Page 3 is still in friend number 3. Page 2 is still in friend number 2. Page 2 is still in friend number 2 because we refer to page 2, which is already in the memory. And then the next one is page 0. So page 0 is actually in the memory. So no page fault, right? And the page 3 is still in the memory, so no page fault. We don't change anything. And then we comes with the page 1. Yeah, page 1 is still there. So there's no page fault. Now, the next one is page 4. Okay. Now we find out page 4 is not in the memory, right? Because all the frames has other pages. Now, which page we should replace? Okay. Now, let's take a look at the optimal page replacement algorithm. So in the optimal page replacement algorithm, we actually select the page that will not be referenced for the longest time in the future. Okay. So what are we going to do with optimal page replacement algorithm? So in the optimal page replacement algorithm, we're going to look at the reference string and check each of the page number. Now we select the page that will not be referenced for the longest time in the future. So then we take a look at the page 1. Page 1 will be referenced immediately after page 4, right? So in this case, based on the optimal page replacement algorithm, we're not going to replace page 1, right? Because page 1 will be referenced immediately after page 4. So it's definitely not longest time in the future. Now page comes to page 0. And it comes with page 1. And comes with page 2. So for all the page numbers currently in the physical memory, which page is the farthest in the future?
Page 3.
Yeah, page 3. Not 1, because not 0 and not 2, but page 3. Okay. So that's the key. So we're going to replace page 3. So that's what we do. Okay. Now, this is good because if we replace page 3, then next page is 1. That's the reason why we don't replace 1, because 1 is referenced immediately. And then we don't have any page fault, right? So there's a page fault here, okay? And no page fault. And the 0, it's in the memory, no page fault. And the 1, in the memory, no page fault. And 2, in the memory, no page fault. And then we comes to page 3, okay? Now page 3 is not in the memory, okay? Now, however, this program gonna end quickly, right? Because we only have one more page to reference, and then we're at the end, right? However, if you look at this, the page reference string, only actually 0 going to be next one. So definitely you're not going to replace 0. But for 2, 1, 2, 4, I really don't care which one you're going to replace, because anyway, but as far as you don't replace 0, right? So I can choose, say I can replace page number 1. That's fine, because page number 1 is not showing up in the future. So of course it's the longest time in the future, right? So it's not going to be showing up in the page, the reference string. So I can replace page 1, okay? And I keep page 0, keep page 2, keep page 4, and then there's a page fault here, okay? And then the next page 0 comes. Of course, there's no page fault because I did not replace page 0, right? So page 0 comes, and I keep. So there's no page fault. So how many page fault total? Here. There are only 2 page faults. we can kind of feel that this is the optimal, right? Because if we know the page will be used in the near future, we don't replace. We only replace the pages that will not be used for a long time in the future, the longest time in the future. So that means once we use the optimal page replacement algorithm, once page fault happens, then hopefully in the follow-up, instructions, we don't incur any page replacement. Okay, which is good. This is going to dramatically reduce the number of page faults. Now let's discuss this. What's the advantage and disadvantages of optimal page replacement algorithm? The advantage, it's optimal, right? It's just the page fault is minimized. Okay. Now what's the disadvantage? What's the disadvantage? Any thought? Let me ask you a question. So when you actually, write the program, compile the program, and then we load the program, do you think we actually gonna know which page reference string we're gonna incur? So that means, do we actually know in advance that which page will be loaded first, which page will be loaded second, which page will be loaded third? So in another word, do we have a knowledge of this page reference? Do we have a knowledge of this page reference string? Do we have the knowledge of page reference string?
Probably not.
No.
That's a complicated question, right? Probably not. Particularly if we try to run a program with dynamic linking, right? Because with dynamic linking, we don't even know which is next actually instruction, which is next function we're going to call, and which is the next actually memory address we're going to access. If we don't know what's the next memory address we're going to use, how should I know what's the next page we're going to use? Because we need to know which memory address we're going to access. Then based on the memory address, we can find out, oh, what is the page we need to load. But if we don't have these, page reference string, it's impossible to implement the optimal page replacement algorithm. Now, it's possible though, if we can decide the sequence of the instructions during the compiler time. So once we actually finish the compiling, but still it's kind of difficult, because once we load the program, after even just compiler time, we know exactly what's the order of, reference string. And then when we load it, we still don't know. Yeah, in that case, we know exactly the page reference string. Okay. But implement optical page replacement algorithm is still kind of tough, because it requires, every time we need to remember which one is the farthest. Every time one page fault happens, we need to actually check. So the performance is one thing. It's impossible. It's not always possible, because if there's involved a dynamic linking, then we don't actually have these page reference string, okay? Because which page will be loaded is depend on at the runtime. So at the runtime, we then know which page will be loaded. But even with like a statical, memory actually mapping, it's still kind of tough, It's possible, but it's tough. Okay, it takes time. So technically, optimal page replacement algorithm will not be used. Okay, we will not use the optical page replacement algorithm. However, optical page replacement will be used as some kind of for comparison purpose, like for benchmark. So if we try to compare any page replacement algorithm, we just compare this page replacement algorithm with the optimal one to see if we are closer to the optimal one, and then that's a good one. Okay. So here's the advantage and disadvantage. The algorithm is guaranteed to generate the smallest number of page faults for all reference stream, which is clearly the case. However, the algorithm is unrealizable because the replacement decision depends on future reference, which are unknown at the runtime, particularly if it requires like a dynamic linking. That's definitely not possible. Okay, but the algorithm provides a useful lower bound at the number of page faults for comparison with other algorithms. So you can use this as a benchmark or some, So then let's talk about another replacement algorithm. That's called Fifo. Remember the Fifo, right? In the process, in the process management, we also use Fifo in the first come, first served. Okay, in the multi-programming environment. Okay. Now the reason that we also use the Fifo in the page replacement is that Fifo is always the easiest one to implement. Okay, and the easiest one to understand. Okay. So let's say when we use Fifo, the Fifo basically use a queue. Use a queue. And we have the head of the queue. So that's the head of the queue. And that's the tail or the end. Sometimes we call the tail. So again, let's take a look at the same example. So initially at the time 0, and page 0, 1, 2, 3 are loaded. Page 0 loaded in frame number 0, page 1 loaded in frame number 1, page 2 loaded into frame number 2, page 3 loaded into frame number 3. Okay. And suppose that each time when we load a page, then that page will be placed at the end of the queue. End of the queue. So in this case, suppose page 0, page 1, page 2, page 3 was loaded in that order. So that means page 0 is loaded first. Page 1 is loaded next. Page 3 is loaded. Page 2 is loaded third. And the page 3 was loaded last. So then page 0 will be at the head of the queue. Page 1 is next. 2, 3. 3 is at the tail. Okay. Now, when we comes to page replacement, we always replace the one at the head because the head was the very first one that was loaded. Now, once we replace the head, and the next one becomes the head. So we push each of the page forward. So once the page 0 was replaced, and then page 1 will push forward to the head, and the page 2 will be next, page 3 will be next. So we always maintain a queue, and the head of the queue is the oldest page that was loaded, and the tail of the queue is the newest page that was loaded. So initially, when in this page actual reference string, so we have a 2031 and 2031. These 3 pages are loaded, so we don't have page replacement, right? Same thing. No page replacement. Now we comes to page 4. Now page 4 happens. Now when page 4 needs to be replaced, now which one will be replaced? Very simple. The page at the top will be replaced, right? So then we replace the page 0 and keep page 1, 2, 3. And then we're going to update the queue. So now page 1 is the head of the queue. Page 2 is the second. Page 3 is here. And the page 4, which was recently loaded. So page 4 is at the tail. Does it make sense? Okay, so the next one, page 1. And then we find out page 1 is currently in frame number 1, is still there. So there's no page fault. Now we come to page 0. 0 was just replaced. It was there, but now it's replaced. Now who will be replaced next? Which page will be replaced next?
1.
Okay. One will be replaced. And then we push the queue forward. So 2 will be the head. 3, 4, and a 0. 0 was just loaded, right? That's the reason why I don't like a Fifo, because next page is 1. So I just replaced the page 1, and then page 1 will be called again, is referenced again. Okay. Now who will be replaced next? 2, right? So I'm gonna replace 2. That's the worst scenario, right? So I just replaced the page 2 with page 1, and then page 2 is referenced. So after replace the page 2 with page 1, then page 3 is actually pushed forward to the head, and 4, 0, and 1, right? So now page 4 is the 3 is the header, and then the next one, page 2 was just replaced previously. So then I'm going to replace page 2 with, okay. So page 2 actually is referenced. So I'm going to replace page 3, right? So I'm going to replace page 3. So each time when I do the replacement, I need to keep track of this. I need to keep track of this queue, because the page in the head of the queue always going to be replaced, and then shift the remaining pages forward. That's really the worst scenario. I always replace the page that will be called next. So page 3 comes, the 3 was just replaced by 2. Okay. Now page 3 comes, I'm going to actually replace the page 4, right? So 0, 1, 2. So page 4 is replaced. So page 0 pushed to the head. 1, 2, 3. And the next one, it's okay because page 0 is in the memory, so there's no page fault. So let's take a look. There's no page fault, no page fault, no page fault, and there's a page fault, no page fault. And there's page fault, page fault, page fault, page fault, no page fault. I have a total of 5 page faults. And these 4 cases are the worst case. Every time I replace the page, and the next one, that page was referenced next. And then I replace another page, and another page was referenced. I replace another page was referenced. So I always replace the one that will be used. So this is actually a nightmare. Now, this is actually kind of extreme situation. Normally, Fifo actually the performance for Fifo is not really that bad. Because in the typical scenario, when we run a sequential program, when we execute the instruction one after another, normally, because of the locality, so there's no really, it's not, the real actual page replacement would not be always like this. This is the nightmare, okay? This is really a nightmare. We don't like this. But most of the time, it's not like this. So the Fifo page replacement, it's easy to implement. You just need one queue. And then every time page replaced, remove the head of the queue and push everything forward. Just shift everything forward. So it requires only a single pointer to designate the oldest page in the memory. When the page is replaced, the pointer is advanced to the next frame, like a modulo of n. So the n is the size of the physical memory. Fifo algorithm takes advantage of a principle of locality, except for branch instruction. The branch instruction is really not predictable because if you have an if statement, a while loop, so you're going to jump back and forth. So that means you're probably going to execute the instruction in page 1, and the next instruction is going to be in page 100 because, you're going to actually jump the instructions. It's not. And after you execute this instruction, the next instruction is not the next in the next memory address. It's probably going to be in a memory address 1,000 miles away. So as execution advances sequentially through the code, the likelihood of referencing a page used in the distant past diminishes with time. So that's why Fifo is still not a bad option, okay? Now there's another page replacement algorithm that's called least recently used. Now tell you the concept because we're running out of time. The least recently used page replacement algorithm, basically so suppose we have the same kind of situation. We use the queue, but when we have a page replacement at 4, so we don't have change here. Now, we basically look at not look the future like the optimal one. Okay, we look at the history of the reference. If a particular page was referenced recently, don't replace it. One is referenced recently, and 3 was referenced recently, and 0 was referenced recently, and if 2 was the farthest in the past. So then we replace 2. Now, I'm going to explain why, what's the logical behind this LRU, the least recently used one. Okay, that's something we're going to discuss next week, next Tuesday. Okay. So do you have any questions?